In this video, I want to take a look at linear operators, remind you what they are, and then show you how it is we're going to use them to simplify some of the work that we have to do in solving nth order non-homogeneous differential equations. So we have talked about linear operators before in the sense of linear algebra. A operator is a mapping from one vector space to another. A transformation is a mapping from one vector space to another. An operator is a transformation from a vector space to itself. So from our point of view, we're dealing with functions, the vector space of functions, and something like the derivative is an operator because you plug one function in and you get another function back out again. Okay? And it has the following properties. In fact, any transformation is called linear if it satisfies these two properties. That is, the transformation of the sum of two things is equal to the sum of the individuals transformed. This is called the additivity property. It almost looks like the distributive property that L just distributes over addition. And there's this thing called the homogeneity property where L of a constant times y is the constant times L of y. Essentially, the transformation commutes with scalar multiplication. So it distributes over addition and it commutes with scalar multiplication. This is what makes a linear transformation. Now, if that transformation is an operator, this becomes a linear operator. Okay. The derivative is an example of a linear operator. And when we're looking at differential equations now, we're looking at these like higher order differential equations, but we're only looking at linear ones for the moment. And the linear ones are things that look like this, where here's a third order. You've got the function y times some p of t, some p3 of t, and I'm using capital D's here to just indicate this is an operator notation here, right? That d of y is the derivative of y. D squared of y is the derivative of y. So the second derivative, and d cubed would be the third derivative. So I've got a third order differential equation here. But the left-hand side is a linear operator. The thing is multiplying by p3, right? If this y was a y1 plus y2, like that thing, well, when you multiply by p3, the distributive property says, sure, multiply y1 by p3 and multiply y2 by p3. So that distributes. Likewise here, the derivative distributes over addition, and multiplying by p2 distributes over addition, and likewise the second derivative and the third derivative. This whole thing here is a big old linear operator, and so I just call it L of y. Now, what we need to look at next, and this is why we're doing this, is that in many of the problems that we're about to do, g of t is not just a simple function, but maybe it's a sum of some things. Okay. So I might have a differential equation that looks like this, where you've got a sum of two things over here. What this allows us to do is it's going to allow us to say, let's look at two simpler differential equations. Let's look at just L of y equals g1 and L of y equals g2. Find a solution to this first one, call it y1. Find a solution to the second one, call it y2. And then notice that if I apply that left-hand side, that linear operator to y1 plus y2, because it's a linear operator, it satisfies this equation, which then the L of y1 is g1 and L of y2 is g2. And what you have is that y1 plus y2 is a solution to the more complicated differential equation with the g1 and the g2 added. So I can do them individually and then add my results. And we should now do a couple examples of that, but we'll do that in another video.